This is what I was talking about when I said, alright, so it started, okay, so this is the exhaust gas from the cylinders, like after the combustion cycle. So what the turbocharger does is it feeds it into a turbine, and then that like creates work. And then at the same time, like fresh air is like sent into a compressor, which like requires work. The compressor increases pressure. So the work from the turbine, like from the exhaust gas, which spins the turbine, like is used by the compressor. That compressor, then there's also a scroll, increases pressure even more. So now like this air that came from the outside is compressed and scrolled. That makes it like super hot, so much heat, so much pressure. So then it needs to be cooled because you can't send it into the chamber like hot. So like this water comes and takes all of the heat, and then that air goes into the like cycle and then produces the exhaust gas. So that's like one cycle right here. It produces this exhaust gas. So it's self-sufficient. But now the cooling water is hot and we need to use it again, so we need to cool it down. So it goes into like a radiator, and then the heat like leaves the system through like heat energy. So I was talking about this heat. I want to like save this heat and like put it back into the turbine. So like this turbine can be even like maybe even generate power, be self-sufficient more often. Because it's not always it's only self-sufficient when the load on the engine is enough. Otherwise,
did you run it by folks, and what were their thoughts?
Yeah, I did. They thought it was. It's a good idea, but it's also like just impractical. But there wasn't a way for me to know that. Like, there's not enough to be harnessed here that makes like it worth the cost of like building something that harnesses it. But this is me trying to figure it out with thermodynamics. So like you have the air. So right here, you have the air and the cooling water. The heat from the air, like from phase 1 to 2, goes into 3 to 4. So I was trying to find out like properties of them at different points. And then like I backtracked. I did it a couple ways. I'm not gonna get into the details really, but
yeah,
this down here was me. So state 0 and state 1 is like before the compressor in the first place. So like I like looked up values. So the very first air that goes into the compressor is atmospheric, so it's like 1 bar. This is the average temperature of the atmosphere, which I looked up. Got this. I found the enthalpy for that in my book. I did some stuff. I found out that the temperature in the compressor, like after it comes out of the compressor, is this was wrong. I did something wrong. I didn't write the right answer, but I found out it was around 300, which was right. That was kind of cool. Okay, this is where I actually figured out the thing with that. So I like the work is equal to mass flow rate times change in enthalpy for like a compressor and for a turbine. Except the compressor like requires work input and the turbine makes work output. And enthalpy is dependent on temperature. So then I didn't write it out here, but in Excel I like plotted everything, and I found that at high temperature enthalpy so at low temperature it looks like a 1-to-1 relationship, like enthalpy and temperature are the same. But that's not actually true, because I noticed that higher temperatures, like around 1,000 degrees, enthalpy like outclimbs the temperature. So my thought was that in a compressor, like the work is equal to mass times delta, like change in temperature.
Right.
And then in the turbine, it's mass times change in enthalpy. So I was thinking, if the enthalpy is like climbing higher than temperature at those high temperatures, then you produce more work from the turbine than you require for the compressor. And then that is like, that's good. That's what we want to do.
So this is your
see, here's a like a graphical thing. So this is the top is, so the dashes are enthalpy and the dots are temperature. So like at 0 degrees they would be exactly the same. At 220 degrees, which is like where that excess heat comes out, enthalpy would be barely higher because of like it outclimbs it a little bit.
Mm-hmm.
But then as you get to higher temperatures, enthalpy starts, like the gaps get separated. So at this high temperature, I wanted to use like the space between them, this amount of power.
Gotcha.
Yeah, but it's a dud. It doesn't work.
It's okay. I mean, you know, the key is that you're thinking. Okay. And I want to ask you, like, so what company is this again you're doing internship with?
Progress Rail.
Progress Rail.
Caterpillar, basically.
And
yeah.
And what is your experience so far? 3 days into it, as a sophomore coming out, are you getting some traction?
Yeah, I think I've learned a lot already so far, which is nice. But I look forward to running tests and building stuff this summer.